The Sahara used to be green, so why don't we just bring it back? We could pump water beneath the sand, plant billions of trees, and turn an area nearly the size of the United States into forests and farmland. It sounds cool and interesting, but if it actually worked, it might damage the rest of Earth, because the Sahara quietly controls things happening thousands of kilometers away. Change too much of it, and we could disrupt systems most people don't even know exist. Worse, the project might start heating the planet it was meant to cool. And the real danger wouldn't begin when the trees died, it would begin when they survived. So could we really terraform the Sahara? To answer that, we need to go back around 10,000 years because the Sahara has done this before. Large parts of it once had lakes, rivers, and open grasslands. People raised cattle there while hippos and crocodiles lived where enormous dunes sit today. But humans didn't create that world. A slow change in Earth's orbit increased the amount of summer sunlight reaching North Africa. That strengthened the African monsoon and carried rain much farther north. As plants spread, they held moisture in the soil and released more of it into the air, helping the wet conditions continue. Then, around 5,000 years ago, the orbital pattern changed again. The monsoon weakened, the rain moved south, and the green Sahara slowly became the desert we know today. Nature once supplied all that water, and to bring the green Sahara back, engineers would have to replace the missing monsoon with machinery. And that machinery would have to water a region so large that the numbers stop feeling real. The Sahara covers about 9.4 million square kilometers across 11 countries. And it isn't one enormous sandbox. It also contains mountains, gravel plains, oases, and desert ecosystems that already support life. But let's imagine giving the entire region 500 millimeters of irrigation each year. That would require roughly 4.7 trillion cubic meters of water annually. For comparison, humanity currently withdraws close to 4 trillion cubic meters each year for our homes, farms, and factories combined. There's plenty of groundwater beneath the Sahara. The problem is that much of it collected thousands of years ago and returns extremely slowly. Pump it at this scale, and water levels would fall much faster than nature could replace them. This will threaten the communities already using it. So engineers would need something much larger: the ocean. Engineers would have to line the Atlantic, Mediterranean, and Red Sea coasts with enormous desalination plants. Inside, high-pressure pumps would force seawater through membranes that block the salt. Using today's technology, producing 1 cubic meter of fresh water generally requires around 3 to 4.7 kilowatt-hours of electricity. Apply that to our full irrigation estimate, and desalination alone could consume between 14,000 and 22,000 terawatt-hours every year. And that's before pumping the water hundreds of meters uphill and deep into the desert. Now, to be clear, this isn't a quote for a real project. It's what happens when we apply current energy requirements to the amount of water this plan would need. Electricity alone could cost hundreds of billions or even trillions each year. Solar and wind farms would power the network, while thousands of kilometers of pipelines, reservoirs, and maintenance roads carry the water inland. Underground drip lines would deliver it directly to plant roots, reducing evaporation. Then there's the leftover brine. Dump that concentrated salt water beside the coast, and it could damage marine life. And even if engineers delivered every drop, wet desert ground still wouldn't become a forest. First, they'd have to build the soil. Because pouring water over sand mostly gives you wet sand, living soil also needs organic material, usable nutrients, and microscopic organisms. In looser areas, it must remain stable long enough for plants to take root. So crews wouldn't begin with an enormous rainforest. They'd start with native grasses, shrubs, and drought-resistant trees. Their roots would hold the surface together while fallen leaves and dead vegetation slowly add carbon to the ground. Small stone barriers, trenches, and shallow basins would catch rare rainfall before it runs away or evaporates. Over time, the landscape could develop into a mixture of farmland, grazing areas, and woodland. A smaller version of this idea already exists along the Sahara's southern edge. The African Union launched the Great Green Wall in 2007. Despite its name, it's no longer planned as one straight line of trees. It now includes farms, native vegetation, and restored land across the Sahel. Nearly 18 million hectares have reportedly been restored. The target for 2030 is 100 million. Funding and coordination have already slowed that project, and it sits along the wetter edge of the desert. Still, if enough vegetation survived, it might begin doing some of the work itself. Plants don't just take water from the ground, they also release some of it through their leaves as water vapor. That moisture rises into the atmosphere, where it can help form clouds and eventually return as rain. Vegetation would also make the surface rougher and darker, changing how heat and air move above the desert. In 2018, researchers tested something similar inside a climate model. They covered enormous areas of the Sahara and Sahel with simulated wind and solar farms. Those installations changed surface heating and air movement, producing more rainfall and vegetation, especially across the Sahel. In some regions, that could create a helpful cycle. More plants release more moisture creates more rain, and more rain supports more plants. But this happened inside a computer model, not across the real Sahara. The driest areas might still need permanent irrigation, and that darker surface helping to create rain would also absorb far more sunlight than the desert it replaced. Scientists call this reflectivity albedo. Bright desert ground sends more sunlight back toward space. Dark leaves, wet soil, and solar panels absorb more of that energy instead. So as the Sahara became greener, North Africa could begin holding on to more heat. But that doesn't automatically mean the entire planet would become warmer. Plants release water vapor, which cools the surface. Extra moisture could create clouds that reflect sunlight, while the growing vegetation removes carbon dioxide from the atmosphere. All these effects push the climate in different directions. One idealized desert irrigation model produced more rainfall, but also around 0.1 degrees Celsius of global warming by 2100. Other research into semi-arid forests suggests the opposite. Given enough time, carbon storage and evaporative cooling might outweigh the heat caused by the darker land. So we don't have one simple answer. It would depend on the plants, the clouds, the amount of irrigation, and how long the project continued. Engineers wouldn't simply be constructing a forest, they'd be adjusting a climate system without knowing exactly where every change would end. And some of those changes could travel thousands of kilometers away. Each year, strong winds lift Saharan dust into the atmosphere and carry it west across the Atlantic. NASA estimates that around 27.7 million tons of that dust settle over the Amazon basin annually. Mixed inside it are approximately 22,000 tons of phosphorus, roughly replacing the amount washed out of the Amazon by rain and flooding each year. More Saharan material falls into the Atlantic, supplying nutrients to parts of the ocean ecosystem. If vegetation covered the desert's major dust-producing regions, roots would hold the loose ground together and reduce that flow. That wouldn't make the Amazon suddenly disappear, but it would change an important nutrient supply, and nobody could guarantee what the wider effects would be. A more careful project could leave major dust-producing areas untouched. By this point, though, we're no longer terraforming the entire Sahara. We're deciding which parts of a living desert we're willing to change. And the wildlife isn't the only thing already living there. And that brings us to the people. The Sahara isn't unused land waiting for somebody to redesign it. Pastoral families move their animals across it. Trading routes connect desert towns, and entire cultures have adapted to surviving in this climate. The desert also supports around 500 plant species, 70 mammal species, 100 reptile species, and 90 bird species. Creating forests and farms would attract new wildlife, but it would also remove the open, dry habitat that existing species need. Pipelines, roads, fences, and new settlements could interrupt animal migration and traditional grazing routes. And we also have the political problem. The Sahara stretches across 11 countries. Their governments would have to agree on water rights, land ownership, construction costs, and who maintains the system decades later. People living there couldn't simply provide the land for someone else's climate experiment. New jobs and farmland could improve their lives, but only if they controlled the project and received its benefits. That doesn't mean greening the Sahara is impossible. It means the realistic version would look very different. We already have the technology to restore selected parts of the Sahara. Engineers could expand one monitored area at a time. If groundwater started falling, temperatures increased, or concentrated brine damaged the coast, they could change the plan before moving farther. So yes, we could make parts of the Sahara greener. Turning the entire desert into a rainforest would require more water, energy, and coordination than we can realistically provide, and the climate consequences remain too uncertain to control. Now, if projects like this are your thing, you would love to watch our other video, Can We Really Build Space Elevators? In that video, we figure out how a 96,000-kilometer cable could hang above Earth, how an elevator would climb it, and what's still stopping us from building one. It's already on the channel, so check that out. And subscribe to the channel if you want more engineering ideas that sound impossible until you see how they might actually work.